Okay, afternoon everyone. I'm Alex Fry. I'm a colour and imaging engineer from Industrial Light and Magic in Sydney, Australia. I'm Jay's man on the ground down under. And as well as that, or as part of that role, I was also the co-chair of the Output Transforms virtual working group, which was tasked with developing the new set of output transforms that are in ACES 2.0. During that same period, I was also lucky enough to be a compositing supervisor on the animated feature Transformers 1. And at this point, if we had more time, I would play a reel hyping everyone up with a bunch of cool pictures from the film, but we've only got 20 minutes, so I'm going to kind of blast through this a little bit. So what is ACES? I realize I'm using the old branding. I didn't realize there was new branding, but I learned something new in the previous session. So ACES is the Academy Color Encoding System. It's a set of defined color spaces. The two important ones are ACES AP0, the interchange space, ACES 2065-1, and the working spaces that we all use in the industry, which are ACES AP1, ACES CG, and the log version, ACES CCT. The block diagram looks something like this. We start with some piece of colorimetry on the far left. It could be from a camera, it could be from a CG render. We go into what's called an input device transform. We move into the defined ACES color spaces. We do some work there of some description. And we then optionally pass through a look modification transform, or an LMT, which might be a CDL or something more complicated. And then we pass into the output transform pipeline, which is in ACES 1 made up of the RT and the ODT. The RT is your virtual film stock, and your ODT is sort of a technical transform to get you down to the specific display that you're trying to display on. Now, a real ACES workflow looks more like this, with many different input input media passing through many different input device transforms. They all come into the single unified space, and then on the way out, we go through a single RT and then many different ODTs. The part that the Output Transforms Committee was concerned with is just this section at the end. So this is the only part we were looking at, but we were trying to re-engineer this part of the system. So I was co-chairing this with Kevin Wheatley from Framestore, along with a lot of assistance from Scott Dyer and Nick Shaw, and then we had other major contributions from Pekka Daniele from Filmlight and Jed Smith, as well as a host of other people who came and went along the multi-year process that this took. So what is a DRT, a display rendering transform? So color spaces in the post world can be largely grouped into two major categories. We have scene-referred color spaces, where what we're trying to do is describe the color coordinates and the light intensities of the thing that is on the far side of the camera, the scene. Now, that could be a real scene that we're shooting with a camera, or it could be a CG imaginary scene, but either way, it's the thing on the far side of the camera that we're trying to describe with the numbers that we're passing around. We then have the second major category, which are display-referred color spaces. So this is where we are often with similar coordinate systems, similar encodings, but conceptually we're trying to describe the light that's coming out of the screen, the light that is display-referred. But to move between these things, one where we have near unlimited dynamic range and all colors are possible, the scene, we need to squish that down and get it onto a screen that we can actually manufacture and reproduce and display an image on. So that's the display rendering transform, and that connects the two. So ACES 1.0 has a DRT, but what's wrong with it? So years ago, there was a paper called the RAE, or ACES Retrospective and Enhancements paper, and this was a collation of a bunch of industry feedback describing the little issues and niggles that everyone was having with the ACES system. Now, ACES 2.0 is largely meant to address that. The only part I'm going to talk about today is the issues that we were trying to solve with the output transforms. So the key design goals for us were to improve the consistency of the tone scale, having a single parameter that would control it across all dynamic ranges, to unify the structure for all the different transform types, to minimize the hue skews across the exposure range, to have robust gamut mapping for extreme out-of-gamut colors, to fully fill the extents of the output display cube, which is important for some reasons we'll go into later, to be fully invertible, which is an extremely useful property for a display transform, to be neutral, which is incredibly hard to describe, and everyone has different feelings about what that means, but that was a goal, and it has to look good doing all of those things at the same time. So the notorious 6 constantly come up as an issue when we're talking about how these things work. And this image here, it's an extreme case. This is a sweep of AP1 color values, but it tries to illustrate the problem that we're having here. Now, a lot of normal imagery doesn't show these extreme problems, but the extremes are where people have issues. So the middle band here is a sweep of AP1 colors. To the left, we're exposing down. To the right, we're exposing up. Now, you'll notice even the normally exposed one has some issues. We've got big blocks of blue values where there are many different blues in there, but they're all collapsing into a single shade of blue. Same with the green. And as we expose up, we are staying blue if we're right on that axis, but we're not actually communicating any increased intensity. You can't tell that the blue on the far right is any brighter than the one in the middle. If we fall either side of that, we're also having an issue where a blue will skew off towards cyan or skew off towards magenta, depending on which side of that boundary we're on. Same thing happens with red. It either becomes magenta or becomes yellow. Now, there's two different reasons that's happening. The first is RGB per channel lookup skews. So if we have our scene linear data, it increases. We want to bring it down so it fits within whatever our display device is. We apply a tone curve to it. Now, if that's on a black and white image, that kind of just works, and everyone's happy. If you do it to an RGB image, each of those channels are having the tone curve applied independently, and they're each interacting with that curve at different points. Now, with an RGB system, the proportion of those differences between those channels is what makes a color a color. But if they each interact with that curve at a different point, their proportions relative to each other change. So as you roll off, you change color, which is highly undesirable if you're trying to keep a consistent image. The second problem with that is that in our modern world where we're trying to hit SDR displays and HDR displays at the same time, the rate of that change is display device dependent. So you'll have one set of hue skews on an SDR device and a different set of hue skews on a HDR device. Sometimes we can lean into that. You know, there are plenty of images that get worked on where those skews become part of the creative intent. And we often have to do a bunch of work to maintain those hue skews that were sort of established and worked with in the SDR domain and have them still take effect in the HDR domain, which requires a whole bunch of fairly awkward LMT jiggery pokery under the hood. But there are other situations where we just don't want those hue skews. One of our main characters has red eyes. We want them to stay red regardless of their exposure level, and we want them to be red in SDR, and we want them to be red in HDR regardless of where they're hitting that tone curve. There's also gamut clipping skews. So these are due to the way the tail end of the old output transforms worked, where once the tone curve had been applied, there was a straight clamp down to the display primaries. Now that meant you lost a bunch of subtle variation within there, and also the color would change depending on which one you were targeting. So if you were clamping down to P3, it would skew one direction, and if you clamped down to Rec 709, it would skew in a different direction. You would lose information, but it would also change color, because P3 is not just a more saturated Rec 709, it's a different color entirely. If you want to see both of these problems combined, if you watch any F1 wet race, you can see it really easily at the back of the car. So you'll have a really bright red light that is suffering from the per channel roll-off issue, where what is a red light becomes yellow. And you also see the collapse issue, where we've got red light casting into the white spray. It should be brighter. It's got more light hitting it, but it's actually becoming darker because the red light's hitting it, which makes no sense in the real world. That would never happen in reality, but it happens through display transforms all the time. We're trying to make something that's simple, neutral, and looks good. I'm sure everyone's worked with many different show LUTs that look nice for a particular film, but they often have constraints that make them unsuitable as a general purpose transform, like ACES tries to be, or the ACES display transforms try to be. So this is a real show LUT from a real show, and you'll notice you can't hit a full blue, you can't hit a full green. It's a bit hard to tell on this projector, but you can't even hit black. If you look at that display transform within the extents of a Rec 709 cube, you can see that almost 50% of the potential values you want to hit are completely inaccessible. This is another display transform from a well-known camera manufacturer. It's very attractive, it works well with their particular footage, but again, there are parts of the display cube that are completely inaccessible, which make it very tough to use as a general purpose transform. This is the display fill of the original ACES RT. It fills the entire cube, but you can see when we look at this, there are some costs with how we got there. We also wanted to have a unified architecture with a more relaxed tone scale. That RAE document I talked about earlier made it very clear that the general industry feeling was that the original one was just a touch too crunchy at the bottom end, so we've just calmed it down there. It's easier to add more contrast in post. It's hard to take it out when your display transform dictates it. But if we jump back to this slide, the unified architecture, this image is actually a lie. This is not how it works. Currently, the HDR ones, or in ACES 1, the HDR transforms had a totally different code path called the SSTS. And it meant that we sort of had a fork with how the two things behaved, where SDR transformed used a separate toe and shoulder curve. The SSTS had a unified curve. They just forked a long time ago, and it was time to bring them back together. So we had two different tone scales originally. Daniele from Filmlight proposed a new one, which we've referred to as the Daniele Evo curve. That's what's in the ACES 2 transforms. We've now got this. It's a continuous function. It's able to move seamlessly from 100 nits all the way to 10,000 nits. We've just got to apply it to our image. Now, we got pretty hung up on this issue for a while. And you can imagine over the years we probably spent 6 or 8 months just churning on this issue, navel gazing, what is an image, what is reality, what is tone. But eventually the solution we came up with was to transform into a cam space and do some of the work there where we can manipulate the brightness independently of the other components, and we have something that we can refer to separately as tone and do our operations on. Initial prototypes used a cam called Zcam, but we ended up switching to another one called Hellwig-Fairchild 2022. It was mathematically a little bit simpler, and conveniently we also had access to Luke Fairchild, who was the PhD student who'd been working on the project, which made it much easier to have access to the source. So the components that we were interested in were the lightness, which became our in isolation tone, our hue angle, and our colorfulness. Our JMH components. So we do all of our work in that space, and we start building stuff. So this is what the ACES calls looked like for years. We would all be online, me at 6 in the morning, some other people at 10 at night, some people having a more relaxed midday. And we would prototype stuff and build stuff. We would do most of the work in Nuke. Sometimes we'd be building it out of raw Nuke nodes, just matrices and color lookups. Other times we'd be doing stuff in expressions. Eventually we moved to doing stuff in Blink script once it hit a certain level of complexity. And there were multiple prototypes that were being worked on. So we had a version that was really just a slight warming over of the original transform. We had the CAM approach. Jed Smith had his Open DRT, which still lives on today, separate from the ACES process. Some of the time we're building display transforms. A lot of the times we're just trying to make scopes and visualizations to understand what the data is doing as it passes through the system, because you can't just look at images. You've got to see how this data is shifting around and moving around inside the transform to get a proper understanding of what it's doing. A lot of time trying to work on the compromises. How does it invert? Do the values explode in one direction and work fine in the others? A lot of tweaking. We had something that worked pretty well pretty quickly, and then spent the next 90% of the time trying to get the last 10% done. So it did drag out for a long time, this process, but eventually we came up with something that looks like this. So we take our RGB input data, we go through our CAM into JMH, we apply our tone scale just to the J component, which means that we are leaving hue and colorfulness stable. We have a chroma compression step. This is the most subjective part of the whole transform. This is where we sort of bring certain values under control, leave others alone, try and protect skin tones, get the neons under control. Then we have a technical gamut compressor, which pulls stuff into the final display hull that we're working with. And then we really just prep the thing for display after that. So we're trying to do as little as possible, but making it fit where it needs to fit, which is the trick. We spent a lot of time testing with pathological images that came out of the reference gamut compression development process. So this would all be fine if all of the colors ended up where you would want them to be on this diagram, but a lot of RDTs are optimized against normal reflective scenes or Macbeth charts or things like that. And the consequence of that is out at the edges, things sometimes get a bit squirrely, and narrow bandwidth emitters or other supersaturated things can end up right out at the edge or beyond the edge, which is even more problematic. So different cameras have different gamuts, and they can often land data in undesirable places. So we were trying to develop something that was much more tolerant of these out of gamut colors. So red cameras often will land data outside that yellow boundary. RE cameras will often land stuff off the bottom left corner, strange blues, which are very difficult to deal with. The data is real, it's just sitting in a funny position once it's moved into the ACES space. And often we have very weirdly formed CG images. So this one here may look normal, but you've got an ultra narrow bandwidth surface on the dragon, which makes no sense, and effectively an AP one blue and red for those balls, which makes no physical sense, but it's actually pretty common in real CG production where people will just wang the color slider all the way to a corner and hope it works out okay. Now, doing this with a cam makes things a bit tricky because cams are built on real data, so they make sense for real plausible colors. But once we sort of get off into those imaginary zones, we are starting to ask questions about what do things look like when you're off the map? And it's kind of a meaningless question to ask. So we have to modify the cam, loosen up some of the parameters and make it still behave the same way for plausible colors, but not explode when we're in plausible space. And there's other questions, especially with CG stuff, about what should things look like if someone wangs the color slider all the way out to the AP1 primary? You know, should it be the most saturated it can be? Should it be the same hue as a Rec 2020 green, which is actually quite a bit more cyan than a Rec 709 green? We've always privileged hue accuracy over saturation, and we've always prioritized the preservation of intensity over saturation. Which is a bit different to how the previous one worked. We will always try and communicate more intensity if we can. So invertibility. Now, this is something that a lot of the camera transforms don't have to deal with. You know, we are trying to make a transform that can be used in lots of different ways. So we can pass through the forward direction through the DRT from our scene referred state to our display referred state, but it's incredibly useful to be able to go the other way and have a display referred image pass back through the transform in the other direction and end up with plausible scene-referred values again. Now, I've just been talking about how we want to grab all of these values that we're out of gamut and get them on screen, but the catch there is you then have the problem that the inverse transform now wants to spray that data back out beyond your working space. And in a world now where we all work in AP1 for the most part, that's a bit untenable. We don't want to be inverting into negative numbers all over the place. So we have to decide how far out we want to reach. We could plausibly go all the way out to AP0 and say that's our input, but there's a bunch of nonsense numbers in the top left and the bottom left that we would then be pulling into gamut, which we don't really want to do. There's a more defensible position where we could go, okay, if you get your data into the spectral locus, we can get it onto screen there. That would work, but the catch there is on the inverse path, we're now outside of AP1 again, which with modern workflows that are established, that would be a bit of an issue. So we've ended up saying, no, you have to be inside AP1. You can get there any way you want, whether it's through the RGC or through some other technique that you want to use. But if you get your data into AP1, we will then get it onto screen, and conversely, from the display referred state, we can then invert out and land you within AP1, which makes it workable for actual pipelines. Another tricky area of compromise is the corners. So this shape here is the Rec 709 display hull, but in our JMH space, and we get these sort of pointy corners. All additive displays tend to have this property where they all pinch at the corners. Now, we want to get data all the way into that corner, but we also don't want to cause sort of echoes. If we tune our gamut compressor to really pull in tight, we create a kind of an echo of the exterior hull in the interior of our display. Now, this is sort of most obvious with kind of test patterns, but it sort of shows up as funny little kinks in your display data, and it's not terribly desirable. We could just round off the corners and just smooth out the edges. That is a solution, but if we remember earlier, we were talking about how we don't want a display transform that can't hit the corners. We want to be able to get all the way to the edge. And the obvious reason for that is things like logos. Brands are a bit sensitive about their logo looking the way it's meant to look. So we need to be able to get a value all the way out into that corner to make this transform usable in all kinds of contexts where a logo might be involved or people are being very particular about hitting that corner. So rather than pulling in the edge, what we've done is actually sort of puffed out the outer hull just a little bit. This does give us a few hue skew errors at the edge, but it's a pretty good compromise with making it more usable in those other scenarios. We're spending a lot of time looking at normal images through this whole process, but also extreme images. Thomas Manson-Carl generated this really excellent test image for us, which is a spectral render of a whole bunch of Cornell boxes with really narrow bandwidth emitters. And it's really useful because it's extreme, but it's also it's all physically plausible. So there's nothing wonky out towards the edge here. This is how it's rendering through our new transform, but we can look at this through the old transform, and you can see the near ultraviolet on the second column from the right, how horrible those hue skews are. When we're underexposed, we're completely blue, and as we overexpose, we transition to a messy magenta posterization problem. Through the new transform, it looks like this. Yeah, it maintains that near purple appearance, and everything is much more smooth and coherent up and down the scale. This image here shows the old transform. The outer hull here is the AP1 primaries, the inner hull is Rec 709, and these are the skews that we were getting from the old method for collapsing. So you can see some spots where it kind of accidentally works. You know, cyan does project back towards the neutral axis, but many, many greens are collapsing into the same green. Blues are skewing almost perpendicular to where they should be going. Through the new transform, everything comes back in a nice, smooth way back towards the neutral axis. So we've gone from something that looks like this, where we've got these massive patches of lost information where the primaries are, and these incredible skews as we go up. Now we bleach out progressively towards white as we go up. We have more variation within any of those bands, and it's just a much easier to control image. And also we can fulfill some of those other properties, like being able to hit the extents of the cube, which then has these knock-on effects for invertibility. On the right-hand side here, we're seeing JMH scopes. On the left-hand side, we're seeing YXY scopes, and these are all, top is pre-transform, bottom is post-transform. So we're looking at this stuff all the way through the development process, making sure that it works well on normal images, make sure it works well on extreme images. And that's where we got to. So during the same period, I was also working on Transformers 1. We have iconic characters that have colors that need to stay consistent with the iconic 80s original characters, regardless of the exposure level. We also have our main protagonist who starts off the film with yellow eyes, referencing the 80s Marvel Comics version of Megatron, and eventually transitions to having red eyes later in the film. Now, what we don't want to have is a situation like that, where the image encoding brings me undone, so we're just going to skip that slide. We also have a number of other, we also had a lot of concept art that was being done by Jason Schreier and his team at Paramount, and we really wanted to stick closely to that. But the reality with current production is that so many decisions get made in SDR, but ultimately the final result is a HDR film. The definitive version of this film is the HDR version, but a lot of decision makers along the way are either doing work on an SDR display or assessing work on an SDR display, and we have to have that work consistently between the two. So his work is all being done in Photoshop. We're then trying to match that on an SDR display. And this is sort of a very modern situation where Linux desktop color management and remote desktop solutions mean it's very difficult at the moment to have a true HDR everywhere workflow. But we want to be able to have people making real decisions in the SDR domain and have it carry through to the HDR version of the film. So we don't want to be getting led astray by hue skews that are working in SDR and not in HDR, and vice versa. So for normally exposed images, things are very consistent and match nicely with the original transform. But if we look at an image like this, where we have a red light hitting our characters from the right-hand side, through the old transform, it skews very quickly towards yellow. If we expose it down, you can see that that light is actually definitely red, but as we blow it out, it's skewing very heavily. And again, this is a property that's only true in SDR and is not true of the HDR version, whereas in the ACES 2 transforms, that is a consistent relationship between the two. Similarly with bright effects, we get those skews. Now, effects is one of those areas where there was a lot of leaning into the properties of the old transform. For fire and explosions, people would take advantage of that skew, and it would give a sense of additional visual complexity. But the catch was that was only ever true of the SDR version. You would look at your HDR version, and suddenly you had a really monochromatic explosion or fire element. So through the ACES 2 transform, in some ways they have to do a tiny bit more work, but the reality is that work has to get done, because if you want that visual complexity at all dynamic ranges, it needs to be in the data, not just be a byproduct of the display transform. That's also true of things like this sun here. On the left, we're getting this skew towards yellow. The underlying data, it's all red. Having the sun skew yellow is a valid creative choice, but if you want to have it, you need to put it in the actual data, so it's true of all dynamic ranges. So at the end, it all worked out. We have a nice, high-quality HDR version on home video, and it got HDR theatrical release both in Dolby Vision and in Barco. I will point out that the Barco poster, though, is showing hue skews in the eyes, so you can get this all under control in your own pipeline, but still come undone elsewhere. Now, this here is going to be meaningless on this projector, but this is sort of a before and after HDR and SDR with the new and the old transforms. It doesn't mean anything here, but if you wanted to look at it, I could show people on a laptop up the back or something later if people want to see the difference between these two, both on this material and on the ACES test images. So that's all I've got. ILM are always willing to talk to people who are interested in colour nerdery, so please reach out, or if you're in any other department, we're always interested in talking to people. And if you're interested in getting involved in the ACES process, the whole thing is a volunteer-driven enterprise, and we love to hear more voices at ACES Central. So yeah, that's all I got. Thanks.